Okay. I would accept that too. So presumably the line that was drawn, I assume that's the least squares line. Yes. Least squares fit. Oh, I see. All right. Everybody, Randall.
So, how many people here actually know who Drapeland Design is? Anybody? Anybody? Field notes? Wow. Okay. So I'm gonna basically do this one as a stealing something from him because this is the actual intro to the talk. So I spent a lot of time talking about statistics, and I started doing it in 2008. And Drapeland basically told me that anytime that you give a talk, instead of starting with like something like, "Hi, this is my name, I'm Randall, blah, blah, blah," you should start with a musical intro, which is what this is. This is how we make statistics and data science hardcore. And these were actually all talks that I gave on something related to statistics. And it took me about 5 years to figure out what the fuck I was doing. Until 2013, where we could become the remix of statistics, which as you all know is called, wait, the year of 2014, right? This is actually when we start doing something special. This is the rise of the data scientist. You guys all know it. Kind of like how you were a Ruby programmer with RJS, but now you're a Node.js guy instead. Yeah, that's right. This is the ultimate data science tool. And that's exactly what we're going to be exploring for about the next 30 minutes or however long your attention and that beer lasts. All right? Are you with me? You guys haven't been drinking enough. All right, so let's see if we can get this thing started. Okay, cool. So this is the shameless plug portion. For those of you who don't actually know who the fuck I am, I'm the other black guy in the Ruby community, often confused with Brian Lyles. Do not laugh. Anybody here who was at RubyConf in Denver? Wait, which person was giving the talk? Oh, that's right. I'm sorry. I totally forgot. You're right. Oh, anyway, so Brian and I are often confused, including the time at RubyConf in Denver where Brian was still on the fucking stage and a guy comes up and says, "I love your talk." And I'm like, "My talk's up next." And he goes, No, the one you just gave. And I go, "The one he just gave?" So, it's confused because I work at a company called Thunderbolt Labs. Brian also now works at Thunderbolt Labs. And we made this blog post called Cornering the Rails Black Market because we can. I think we build cool shit. We mostly do it by like talking about numbers and statistics, right? We're really into trying to figure out how you can make numbers work for companies and for businesses. And if you guys actually have something that sounds like a statistical problem, it probably isn't, but you should hire us to tell you that anyway, because that's what we do. We're consultants, right? And I'd like to entitle this talk Decade of Regression. Anybody know why, aside from the line reference? You're wearing an Engine Yard Slayer t-shirt. You better know the fucking reference for Decade of Regression. Well played. So it was because there was an album released by Slayer. Their first double live album was called Decade of Aggression, which, anyway. So I'm going to give you a little ode called In Praise of the Line. So when we think of lines, we kind of take them for granted. I'm pretty sure everybody here has probably been through college algebra, geometry, something like that, algebra 2, right? So you probably remembered lines. We think of them as these things we stand in, we queue, right? I've been spending a lot of time in LA where I realized that when I started talking to people about lines and some of our clients down there, they had something completely different in mind. The price was the same, but it was for our consulting bill. But in reality, the line is like the universal statistical hammer. It's like everything you do in statistics, some way, shape, or form, comes back to a line drawn somewhere, right? Think about Syria. The president said, we have a line, right? Gaddafi had a line of death. You are always dealing with lines. Math is about lines. And so it's the AK-47 of statistics, right? Eventually, if you want to try and figure out what's going on with some data, you've got to draw a line. And so for those of you who aren't statisticians, how many people here actually have a background in math or statistics? Got a couple of you. Okay, I apologize to all of you guys who actually know what we're talking about because I'm about to start lying really, really bad and doing gross oversimplification. So save all those, but that's not true until at least somewhere in between. For the rest of you, feel free to shout out questions. So there are two things that we do with statistics, right? We can actually answer the question of what happened, right? Makes sense. Anybody want to guess what the next one is? It's going to happen. Why? Why is kind of about what happened, but why is really, really hard with statistics? As it turns out, answering why something happened is much harder than answering what happened. You know, correlation is not causation. You might have heard this one. Like, oftentimes you can describe very accurately what happened, but you cannot say why. Canonical example of this one is, remember the Netflix prize? Does anybody remember this? Netflix was giving away fucking shit tons of money for somebody who could make a better recommendation for a movie, right? Napoleon Dynamite. Do you know this part of the Netflix prize? What was it? Who said yes? That's right. So did you guys all hear that? This is an audience participation thing. It's the end of the day. It's like, chime in, raise hands, say stuff. Anyway, so the whole point is Napoleon Dynamite either means everything. Either Napoleon Dynamite is the most important movie in history, beating out Gravity for God knows fuck why, right? Or it means absolutely nothing about your movie selection preference, and nobody can tell you why, right? Okay, listen, how many people have seen Napoleon Dynamite? All right, all the hands go up. Now, how many people like it? Yeah, that's okay. We're biased here because that actually looked like it was about more than about 2/3. Normally, it's 50-50. What's that? Nacho Libre? Okay, you guys really do need to keep drinking. So, in reality, there's a third question that we're not going to address here, and that's what is happening now. It turns out answering that one is really, really, really hard. It deals with time series and actually correlations of what's going on. But I think something that we actually take advantage of all the time is people say things like regression on a variable, regression towards the mean, and data science types like to throw this terminology out there. So the question is, what is a regression, right? Well, it turns out it's pretty simple. It's just a big happy family of techniques for going around and describing a whole series of other techniques that are in a statistician's toolbox that basically tell us relatively how all the data points fit together, right? So at its core, a regression is nothing more than a way of describing how a set of data points relates. As it turns out, doing that, however, can be very, very, very complicated and intricate. So oftentimes when somebody says, we just did a regression on blah, 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 and gave you an answer, what they're really doing is they're kind of saying, this is kind of some hand-wavy bullshit, and I'm not quite sure if you're going to understand it, but I think of my best guess, the regression says that we should watch Napoleon Dynamite, right? So at the end of the day, what we're really trying to do is we're just trying to describe something about the data and then draw some sort of inference, either to tell you what the data is like. So for instance, anybody here Netflix fans? House of Cards? Okay, who here binge-watched House of Cards, 13 episodes? I took up meth just to do that. And if you actually look at the statistics, 28% of the other people also took up math just to watch House of Cards in one sitting, right? So, and the other thing is, you know about the history of House of Cards. House of Cards was actually one of the first data-driven television programs, right? They spent over $100 million producing that TV show, which, if you guys know, that's normally what you pay Sandra Bullock to huff and puff into a fucking 3D screen. So the question comes down to, why would you do that? See, some people did see Gravity. We are going to do a regression later about how much that shit sucked. Trust me, I felt like 12 years a slave an hour in. But that's not the point. So just so you know, Mark's over there. He's here to stop me when I violate the code of conduct for the conference. Anyway, so the whole point of this is that what they did is they looked at the data and they said, hey, we think a political thriller here is going to play really well with what people like. And they made a TV show to fit into a slot that was a gap. It's the same way that Orange Was the New Black got made, right? And so far, not all of them have worked. Frankly, the next season of Arrested Development was not all that stellar, kind of flopped. But for the most part, what they did is they did a whole bunch of regressions on the data that they had, and then they made a prediction, right? So they did exactly what we talked about. They said what's going on, or what happened. People are watching these types of shows. And then they made a prediction about what sorts of shows people would watch next. And then they bet $100 million on it, and they won big time, right? So the thing that you've got to remember is that it's really about trying to know something about the data that you have in your collection. It could be everything from... Yeah. Ordinarily, this is the part where the dog comes up, and I'm about to do something really funny, right? Like touch the electric fence. No, Joey, don't do that. But in statistics, it really is knowing is half the battle, because frankly, it's really hard to know anything about 1 million data points or 500 SQL servers or the 60 servers that you just booted up on EC2, right? So one of the issues that you run into with data problems like this is that it rapidly becomes non-trivial and it becomes a pain in the ass. And regressions quickly become complex, and this is where the line comes in, right? So the line comes in as a great tool for doing this sort of stuff because it got a lot of properties. One is that it's computer friendly. Now, I don't know how many people have ever tried to implement, like, remember like when you think you're all cool and you download one of those computer science papers and you go to implement the pseudocode in the algorithm? How many people have failed at that? How many people fail at it regularly? We deal with mathematics as a standard, and frankly, we don't implement shit. We basically, if we can't find a library that does it, we don't do it. It's effectively lazy because trying to get it right is really hard. So one of the things that actually was kind of fascinating, it's hard to underestimate the real value of having libraries and good quality libraries that have been around since the 70s and are written in Fortran to do this stuff. So anybody who's actually ever installed a math library like R or compiled it from source has basically said, why the fuck am I installing Fortran 7.7? It turns out LAPACK, BLAST, and all these other things were written back in the 70s, and they're so complicated that nobody's wanted to touch that shit since the 70s, right? And when you think about it, does anybody here actually know what the language brainfuck is? Many geek points. Many geek points. How many people here have actually written something in brainfuck? How many people here actually lie about having written something in brainfuck? That's me. So there really is a linear regression library in brainfuck. There's a brainfuck interpreter in R, in the R library. So theoretically, you could, yeah. So you can do linear regression anywhere. You got a COBOL program, not a problem. You can linear regress that shit. Ada, not a problem. You can do linear regression. Pascal, you roll that way, it's fine. You can do some linear regression. So basically, like a good program, you can be tactically lazy about this, right? Another thing is that it's simple to draw pictures, and when dealing with data, you cannot underestimate the power of drawing a picture. You know that phrase, a picture is worth 1,000 words? It's also worth about 100 billable hours. Actually, wait a second. How many people here work for like established companies and don't have to worry about where their next meal is coming from? Okay, so the rest of you should know exactly what I'm talking about. You know, it's like you don't get paid for the equation. You get paid. You know what? This is really good. Well, think about this. This is why Node.js works. Not to like slam on Node.js, right? Because nobody gets paid for how pretty the code is on the back end. They get paid for the little dancing icon that goes across the screen, right? Somebody got paid to put a little clipboard down there that says it looks like you're writing a letter. And if you're consulting, that's what it basically you get paid for, the visual impact of it. So when you're doing data, and we actually have this problem a lot, people hire us because they don't know statistics. We can't give them an equation that has sigmas and alphas and betas and God knows what else, and then basically expect to get paid. We have to draw them a picture. Everybody knows what a picture of a line looks like. We've been doing this since God knows when. First grade, number lines. Second grade, you know, you've got the color line, whatever. You know how to draw a line, and you can easily understand it, and you can probably explain it to your boss, who may or may not have the same interest in the data that you have, right? Like, say, the value of your stock price, or the value of your shares, or the value of your shares and your stock price if you're at Facebook and you have RSS, right? Which leads to the other point. Humans can read the output. Has anybody here actually ever dealt with machine learning, like in an applied sense, or even taken a machine learning or statistics class? Support vector machines, stuff like that? Okay, has anybody actually ever understood what half the fucking numbers that come out of those libraries mean? Well, you almost raised your hand. You're like, no. So, but think about it this way, right? Anybody remember when we launched a probe off to Mars, and then somebody actually put one in yards and the other one in meters, and we lost like a multi-$100 million probe? Right? So think about what it means when you walk into somebody and you say, no, it's 10 to the minus 42nd. I said it's 10 to the minus 42nd. Damn it, man. If I told you there was a Jeffreys tube involved, you'd probably believe me, and you'd probably start getting really excited about that, right? So let's bring this home. Anybody know who these guys are? You should. They are the most expensive TDD company in existence. Knight Capital was a company that put production code into test. No, wait, strike that. They put test code into their production environment and lost $400 million in about 45 minutes. They are what's called a high-frequency trading hedge fund, right? And while this directly didn't relate to their machine learning stuff, there was some of it in there. It related more to the release process. The funny part about that is this could have just as easily happened if they had deployed an algorithm and not quite been able to understand exactly how that algorithm did what it did. Because oftentimes, the more powerful the machine learning or the more powerful the statistical method, the more esoteric and opaque it is. Lines are really easy for people to understand. You can easily interpret them. And to be fair, right, they actually eventually only lost $400 million in 45 minutes, but, you know, some days that happens, right? Like I said, you've got an intuitive understanding of what lines are, and it makes it the perfect place to start with some of the more advanced types of statistical methods. And one of the things that we've seen over the years of dealing with statistics is that what we really have is we have a pretty good understanding of how statistics works, but we lose this gap when we get to the point where somebody says, well, of course it's statistics, and they start drawing sigmas and epsilons and blah, blah, blah. I mean, I don't know if you've ever had this problem, but I remember taking courses with people who were like getting their PhDs and stuff, and it seemed like the difference between what I almost got when reading the book and then listening to them lecture was like, I'm like, this isn't the same fucking book. Am I in the right place? It's like, did I read Chaucer and you guys are actually speaking in ancient Greek? What's going on here? Because people have a tendency not to tie what's going on in a statistical sense to your intuition, right? And as we know as engineers, a lot of what we do, even with testing or behavior-driven development, it's intuition-driven, and we actually have to either find a system or a piece of data that can help confirm or deny that intuition. So it gives us a perfect place to start when we start dealing with really complicated statistical processes, and these things can rapidly get very hairy. So I'm going to walk you guys through simple linear regression, right? This is the point where you can either hoist a beer or take something, or you'll be tested on this at the end, and you won't be allowed any beer tomorrow if you don't know the answers. Lies, lies, damned lies, and statistics, right? So, all right. This is pretty easy. Step 1, formulate a line. Step 2, we actually then do this, right? Step 3, we basically by using either calculus or the geometry of inner product space or simply expanding to get a quadratic in A and alpha and beta, it can be shown that the values of alpha and beta minimize the objective function Q1. Step 4. We then reduce that to this. Voila. We are done. You guys are now officially data fucking scientists. We're done here. You really can actually go get a job as a data scientist now, because frankly, that's what most of them know. So, if anything, that was kind of the short, pithy summary of how I felt most of my statistics and math classes went, right? Does this ring a bell with anybody else? Hi, I don't know what the fuck you just said, professor, and he tells you to go work it out in recitation or talk to your TA, who probably doesn't speak English. So I always call this the mathematical version of just write an Erlang process, right? So instead, what if we were to try and approach this from a more intuitive sense? So let's state the problem differently. We know we have some data that we've seen, and that data, let's just call it X. We know we have some other data, Y, right? You with me so far? I need some nods of assent. Yes? Okay. So what if we just try to figure out what X's go with which Y's? Right? So, all right, here's the first tough test. All right. Come on. So, and not a single person says 42? None of you really write brain fuck then. Come on. Okay, yeah. So the real answer depends on whether you're a frequentist or a Bayesian, right? But who laughed? You laughed. Somebody laughed. That's actually a funny statistician joke. Frequentists and Bayesians. Thank you. Fuck, you tough crowd. Okay, so yeah, 1, right? We intuitively start filling things in. Your brain is going to plug in a 1 whether it's really 1 or not. This is the way things work. We rationally kind of say, there's a pattern here, and this pattern looks like 4 is probably going to be 1. Well, what if we started graphing this on a line, right? Where we said, X is 1, Y is 1, X is 2, Y is 2, X. You get it, right? So even though there isn't a line there, we just had points. If I said to you guys, what do we think the value at 1.5 is, what are you guys going to say? Well, even though there's no data point there, our mind has a tendency to think in linear relationships. There's actually some really fascinating psychological stuff about basically economics, behavioral economics, about how people think in linear terms. It's one of the reasons that gambling works. People have a tendency to assume that the odds are linear when often they are not, right? It's because we think in straight lines. It's not like we think in elliptical curves, right? So here's a harder one. This is the masters in data science. This is audience participation, people. If you don't participate, I don't get to drink. So keep participating. Thank you. All right, 42, right? Well, here we go. This is actually a simple thing where we have another line with another data point. You see where we're going with this? Does this seem fairly intuitive? Are we leaving anybody behind? If the answer is yes, turn in your keyboard. So we already play a mental game of connect the dots, right? And this is the way that we look at these things. As it turns out, as humans, we're really good at doing this. Teaching a computer to do it for us is much harder. But that's still the whole point of machine learning and applied statistics. We're trying to teach a machine to do all the heavy lifting for us. And so the intuitive solution to these sorts of problems is, well, let's draw a line that tries to hit as many of those points as possible, right? That seems to make sense. Yes? Okay. So what we've actually proposed here is that it's possible to describe this data instead of by putting each individual point by using an alternate data model. And that alternate data model is a line. And so anybody remember these things? Yes. This is the audience participation that we're looking for here. All right. Bonus points for naming the font. Lisp? What does that say? You couldn't or no car? No, I can't make a car coulder joke. I could have done better. Actually, I think it is Palatino. It's whatever latex spit out because Jesus Christ, working with that shit's ugly. Is it? Oh, nice. So there you go. Okay, so full bonus points. Well, it's a collaborative effort. You guys, I'd actually ask for a round of applause for you guys, but I'm not sure there's too much audience participation. Hey, all right. So this is the shit we remember from high school, right? This is like every bad Algebra 2 test you've ever had, every single point slope of a line, formulation of a line. But you guys know what this stuff is, and you've seen it for years, right? Well, the problem that we have is that there are very few things that actually run in real life as a straight line, right? So even though we have this ideal situation here where we understand exactly how these things are built, there aren't many things that actually work as a straight line. So the question is, what can we do about that? Because if you think about it, this is actually just as likely for that data model, right, as the other one where we went in a straight line. We never said that you got all the points. Maybe you got some of them. Maybe you didn't get all of them. So we've got to remember that sometimes there are other options, even though maybe this one isn't as likely, but maybe this could have been the actual model that generated those points, and you just had an incomplete data set. We do this to basically prove a point. Regression, any regression, is about trying to draw the best line given the data points and the data that you have. That's about it, and that's all you can say. You can't do the impossible. You can't always be right, but given a certain set of points, you can actually make a set of reasonable, rational decisions about how you can draw a line through those points and what you can infer from that line you just drew, right? So let's try this again. We all remember this one? What is it? Right. This guy measured the world, right? Geometer, earth measure. This is how in a Euclidean plane, means flat, big fancy word, right? You get the distance between where you're at and where you want to go, right? So if you ever tell your friends we're at that bar that's 3 blocks over and 2 blocks up, you're using the distance formula, right? As the crow flies, let's say, a truly random walk. And then we remember our thing of a line. Now, what's interesting here is we could actually assign something different than just these sort of vague random labels like y or big fancy labels like f of x. Remember domain, range, all this other stuff that they always try and get you to say that math is really hard? Well, what if we just call y data? And we call this mx plus b thing, which seems like it's the slope, some x value, and an intercept, right? We'd call that a model. And then because we're now trying to basically draw something we're not quite sure, we just throw everything into another category and we call that error. I'm not serious. This is how mathematicians do this. You know they just make shit up as they go along, right? Well, as it turns out, here's a little bit of our code that does exactly this. It creates a model function that's a line. And then what it really does, that other second red part that's highlighted there, all it's really doing is it's adding a little noise, normal noise. And that normal noise is that Gaussian distribution that we always see, right? The bell curve. How I always like to say most of us got through college. Except for you honor students, fine. I don't care. It's cool. This is basically just adding a little bit of noise to a linear model. So, but don't take my word for it. Let's actually go and see what our intuition tells us. You guys see that? Can you see the data points? So what we did is we actually plotted the true model, which is that line, and then we actually plotted all the points that go around it. And can you kind of see that what we did is we just made a set of points that fall around that line, right? So, I mean, if you think about it, what I said is, if I were a mathematician, I would have said, let's assume a standard linear model of degree 1. And then to this model, we add a standard normal noise with a standard deviation of 3 and a mean value of 0 from a Gaussian distribution to otherwise describe the perturbance around the points of our linear model. Except that I'm a Rubyist, so I sit there and say, let's draw a straight line and then basically splatter some points all around it. Right? Well, it turns out if we then try and using nothing except those points, those random points, we try and fit or draw another line that's pretty through it, we end up getting this blue line here. And what we did is we just go by each one of those points and we calculate the distance formula, right? I think there might have been like 40 points there. Yeah, there are 40 points. So what we did 40 times is calculate the distance formula and then tried to basically draw the line that made the total sum of all those distances as small as possible, right? It's kind of like sitting there saying your friend, unless he's the Incredible Hulk and you can go directly to the bar, you could go 2 blocks over, 3 blocks up. Or maybe you could go 4 blocks over, 4 blocks up, and then come back and come down, right? And you just waste a lot of space. So you're trying to minimize the amount of effort it takes or the amount of distance for all the points that are on that line, right? And the thing to remember is that normally we don't actually know what that red line is, right? If you imagine these are like the timeouts for your SQL server or the amount of queuing that happens for a series of, web requests, you don't know what the true model is. We just kind of assume that it's probably something like that straight line. And we get the blue line when we actually do that fit. And so what we've really done here is we've just drawn a new line that kind of approximates it. And if you see the blue line, it's kind of crappy over by 0, but it gets pretty good, right? It gets pretty close. And that is exactly what all of this does. All it does is it tries to draw a line that's pretty close to what we think that red line is. So if you think about it, if I told you that all this does is it draws a straight line, that's a pretty good guess for another line, you probably would have said, oh, that's not so bad, right? But we have a lot of things that notation that gets in the way of us understanding what our intuition naturally grasps. So there's another benefit of this. Remember that we actually had these equations of lines, right, that we all know since 2nd grade? What do we need in order to draw? What's that? Okay, maybe not 2nd grade. I never told you what mathematical base it was. No. Okay, so like maybe 8th grade, right? 7th, 8th grade. But if you remember, going through basic things, we need either 2 points to determine a line, right? Any line. Or we need 1 point in the slope, right? Or point in intercept. It's kind of the same thing, right? So as it turns out, if we go back to this one, think about this. We have an equation of a line, right? Well, if we go through all this and we have these equations, and I know a point, and I know where that line intercepts because I already drew it, well, I can actually then take some random point x that I have no idea what it is and draw a new line, right? And see where it falls on that line. Now, if I'm a fancy statistician type, I tell you that's actually a prediction. I have known data, right? That's our y-coordinate that I've drawn into some line. Now I have some new random x, and I want to figure out where it goes on this line. Now, if you look, do you see those little purple x's? So those purple x's are actually predictions for a new random value of x based on that blue line. Now, what intrepid soul wants to make some sort of commentary about the purple x's relative to the red line? Why are they all below the blue line? Well, in some instances, they're about on the blue line. In some instances, they're mostly close to the red line. It actually has to do with something called a bias variance trade-off. What it really means is that every time you do something, that perfect model, the red line that we have there, you'll never know. There are very few things that are truly absolutely linear in life, and even if they are linear, there are very few things that you won't measure noise when you measure them in real life. So the predicted points will always be a little bit off from the model. Does that make sense? It's basically, you can never be 100% right. And so those errors, remember that error term that we put at the very end, y equals mx plus b plus e? The e is what basically causes it to drift off that line. It's how far off that line you're going to get. So actually, that's a good question. The question is, do you choose E as part of the model? No. What you do is you actually pick a type of methodology that either does one of two things. It either tries to minimize some criterion like E, like minimize the error, or it maximizes the flexibility for drawing the line. But that's a trade-off. You can't have both. Like, it's kind of like having your cake and eat it too. Something can actually be very accurate at drawing and matching the data points you have, but therefore it is less accurate when it sees new data. You can actually have something that's very flexible about seeing new data, but therefore it's less accurate for describing the underlying model. And so that's basically called it's called a bias variance trade-off in machine learning. What it really comes down to is that there's no such thing as a free lunch. There's always an optimal solution, and that optimal solution is that red line. And in real life, you can get very, very close to that red line, but you'll never actually be exactly on it. Right? So, okay, so here's what this says, right? What we say is the blue line, the dots, the black triangles are what we actually have. The red line is our ideal model that in reality we are saying that we don't know. We're kind of like closing our eyes. And we're saying that the purple X's are the predictions that happen by basically saying, given some new point, what do we get? And so what we're going to say is that for the most part, they come in a different straight line, right? It's pretty close to the blue and it's pretty close to the red. It's actually not a bad prediction engine. So for instance, if we wanted to predict stock prices or which servers we're going to time out, we probably have a pretty good prediction method here. But this was all done using nothing more than the distance formula that you guys know, plus the point slope formula that you guys know. We then told a computer to do the heavy lifting of calculating it 40 times for each one of those points, and then picking a line that basically had all of them. So you can imagine it might have drawn 100 lines, it might have drawn 1,000 lines, it might have drawn 10,000 lines just to pick that one. You with me so far? So another nice side effect about this is that it's really easy looking at something like this to tell when the lines don't fit. You could imagine that if we had one line that was going straight up and down, that's a pretty craptastic model, right? Or if another line was going straight across, it's a pretty craptastic model. Or think about a parabola. Imagine if we had a model where the data was parabola shaped. If we had a straight line, it's not going to be all that great, right? So a nice part about this is that we can actually tell really easily when the model fits and when it doesn't intuitively. With other machine learning methods, like a support vector machine, which is basically uses something called a maximally marginal separating hyperplane in n dimensions. Yeah, right? Drawing, I don't know about you, I have never been able to draw a 19-dimensional cube on a piece of graph paper. Doctor Who might be able to do that. I can't really argue with that. You're right. I would need some better graph paper and probably a better pen. Technically, wouldn't you need it for 19-dimensional? Would you need a 19-dimensional pen for 18-dimensional graph paper, or would you need a That's actually a really good question. It's a mic. You guys have been, Tender Love has been prepping you for this shit all day. Anyway, so this isn't to say that this stuff is perfect, right? There are a lot, like I said earlier, there aren't that many things in life that are linear. So we've got to be really careful when fitting linear models. As it turns out, though, that linear models are so common and so easy to use that they have been extended to almost everything. So linear models have been extended to deal with things that are non-linear, which is really bizarre, right? Linear models can fit non-linear things. At this point, all of you should be basically standing up and screaming in lies and walking out. They can do things, for instance, they can do things where you don't necessarily have lines or real numbers. Normally, regressions are used to predict real valued things, like x for 4.5, y equals 20. It turns out you can actually, there are extensions that will do it when you have things like yes and no responses. Turns out you can actually extend this to when you have more than one response variable. It's called multiple regression or multiple linear regression. It turns out you can extend linear regression to when you have more than one response variable, and some of them are what they call categorical, like short, medium, tall, right? All of these things are actually still solved using the exact same intuition. Turns out you can replace that distance function, the one that we had with the square root of x1, x2, blah, 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 with any sort of distance metric over a space. Big fancy way for saying that if you know how far away two things are, you can still use a regression, like a linear regression, to figure out exactly what it looks like, what the data looks like, and actually how to make a prediction. This is actually technically how something called support vector machines work. They use a linear, basically what's called a hyperspace, and embed all the points that you have in that hyperspace, and then use something called a kernel trick to do a linear transformation of the distance of all of those points. Pretty simple, right? The thing to remember is, while that actually sounds really complicated, and there are huge books and tomes that actually are written about things like support vector machines, logistic regression, all these other regression methods, the nice starting point is at the end of the day, it's still just drawing a line between those points, and that's it. So another problem with linear regression, they're really picky. The models sometimes can do things which is non-intuitive. So imagine you're saying you're going to predict the age at which children first have, I don't know, a glass of Coke. You could get a linear regression model where the number comes out to be -2. At least somebody's laughing at this. When's the last time one of you actually had a niece or nephew that was -2 years old? That are -2 years old? See, this is where so now we have a Bayesian. It might happen. This is actually the whole point of the Bayesian frequentist divide. So just to show you how picky these things are, this is actually a neat example from statistics. So I'm just going to take the notes here. It's like the mean value of each of the x variables is 9.0. The variance of each of the variables is 11.0. That's how wide and spread stuff is. The mean of each of the y variables is 7.5. And the variance of each of the y variables is 4.12. So basically, mean is just how many stuffs cluster around the middle. Variance is how wide that spread is. They all have the same regression line. Okay, this is like fucking weird. Yes, this should be terrifying. How about this? One of these is your 401 fucking K. Right? And your stockbroker is drawing a linear model to predict which stocks are going to sell and which ones he's going to buy. Right? So this is what I mean by they're sensitive. You have to understand exactly what's going on, because if you don't, it's possible to draw some very nefarious conclusions about what's going on here. Like, so for instance, buy or sell. And so this one was actually presented, I don't know, I think in the 70s or 80s as an example of what can go wrong with, basically an object lesson on what can go wrong with linear models. So the point about this is that they're just simple enough to be dangerous, and they're just widely applicable enough that you have to be very careful about how you apply them. So I used to give people huge lists of books to go read on this shit, but now I'm just down to one, because the reality is most people are not going to go get an entire library of $100 Springer Verlag books just to look at this stuff. The best introduction that I found so far to date is this book by Peter Flack. It's called Machine Learning. And what's nice about this is he approaches it from a non-statistician's perspective. It's like, hey, you're a computer scientist. You probably want to teach a machine to go learn something, so let me start teaching you what this stuff is and building up an intuition. He goes about it entirely backwards. Most math books, as you probably know, start with, assume an infinite vector space R, right? And then you shut the book, and then you never open it again. This one's got some really great practical stuff and some really great practical tools, and it's very easy for software developers to pick it up. Another thing, until you get your feet under you, you should not try and do statistics inside a general purpose programming language. Just please don't. You are just hurting yourself. It's kind of like every time you masturbate, God kills a kitten. every time that you try and actually write statistics in C or Ruby, like nothing against Ruby, but we've tried it, it's fucking rough. Don't do it. Don't hate yourself. R is specifically designed to actually help you not blow your own leg off when you're doing these sorts of analyses. So it's a good starting place. And there's a great tool called R Studio, which is an IDE that has like really nice auto-completion and really nice plotting and makes it less annoying than to use on the command line, because R can be very bearish to get working. And we wrote a blog post that actually has more extensive stuff. I don't expect you to actually think about that URL. It's just, but if you go to the blog at Thunderbolt Labs, you'll find it. Like all people who have a blog, it's kind of like we mean to write blogs, but there are only like 10 posts up there. I think you guys can find it. You have a 1 in 10 chance, right? And in fact, if you want, guys can do the linear regression on what are the odds that you're going to pick the right one. So what are we going to leave you with here? My point is, like, data doesn't have to be scary. Statistics doesn't have to be scary. Unfortunately, a lot of people are deeply invested in making sure that you guys who are software developers and software engineers and who are doing the day-to-day stuff, they are deeply invested in making sure that you don't step into that data science realm and start taking their jobs away from them, because the last thing they want is you to basically sit there and say, oh, shit, you're just basically adding up all the numbers for all this stuff and all these points. Well, let me replace you with a shell script, because there goes their $200,000 a year data science job, right? That's all I got for right now. And feel free to always follow us or tweet us, or if you guys want recommendations for other books, drop us an email.